Okay, if you haven't won as second player, you should be able to win by second player just playing enough. If I've won it, everybody can win it. So just go, what I did is I found what I call dead zone times where, and if I have them, everybody has them, where you have 15 minutes in between, like I had 15 minutes right now in between the conference call and the class. I vigorously played. During the conference call, I kind of play like that. So I'm spending my time in between these little dead zones when I'm sitting at my kids' swimming practice. I'm sitting there playing. And so if you find these little dead zones, I know that they have the apps on your cell phone. Just play it until you get enough feeling for it. It's slightly intuition. So I was giving you some of the intuition that I had. For example, I would make these spokes as often as I could. It's kind of hard because their first move is this. You don't want to do this because if you do that, then you're actually setting them up to make either this way or this way to make a long path or long maze. What I wanted to do is make things like this or to cut them off. I would cut them off using figures like this so they couldn't go on a downward trend. Or I would do side-by-side parallel. So I got this intuition of ways to block out the propagation of long chains. So I want to show you why this works in a proof that Dr. Paryzinski would mark up with red. So it's not a formal proof like you'd see in an advanced calculus class, but you're going to see some of those in here. Let's take a breath of fresh air and take a step back and not do that this time. So how this works is if you have m by n boxes, how many total horizontal edge moves do you have? We have m times n minus 1. And how can you see that? It's going to be hard to take notes on, but I want to give you the idea of what. We could just do a 4 by 4. I have 3 on the bottom of horizontal moves I could make. Then I have 3 more here. I have 3 more here and 3 more here. That gives me a total of 4 times 3 moves. So with an m by n box, I'm always going to have m times n minus 1 total horizontal moves. This is counting. And you did a little bit of this in probability, right? You started counting first and then you made your sample. So this is exactly the same thing. This is why we call this combinatorial game theory. Likewise, you have m minus 1 times n vertical edge moves. And you could do the simple illustration I just showed you to understand why that would be so. Wouldn't fly in the Paryzinski class, but it flies here for just explaining what's going on. You could just say, okay, how many vertical moves do I have in the first row? I have 4. Vertical moves in the second row, I have 4 and 4. So therefore, I have 4 times 3. And I wrote this backwards, 3 rows, 4 columns. And that gives me the m minus 1 times n vertical edge moves. So the total possible moves that both players could do simultaneously, if I just sum them up, is going to be, I just multiplied it out, it's going to be all the edge moves plus all the vertical edge moves, horizontal plus vertical edge moves. And doing a little high school commutative algebra gives you this 2mn minus m plus n when you simplify it. It's all fun and games until math shows up, right? No pun intended. So this is like the first few weeks of probability where you're counting and it's all simple, and then all of a sudden you get to a point where all the answers in the back of the book don't match anything that you've come up with. So we're right before that stage. So I copied what you had on the previous slide at the top, so if you're still taking notes, that's where we are. So if a player who completes a box cannot move again, then the first player is going to move last only if the total sum of moves turns out to be odd. And you can kind of think of the horizontal lines that I made the other day. You want to kind of make it so that it's an odd number of moves. So you want that 2m, that total number of moves, to turn out to be odd in order to win. That's if you can't move again, right? But the problem is they've put this wrinkle in there. that even after you complete a box, they make it sound like a treat. You can move again. It's really a bad thing, actually. If you play the game for a while, you realize it's not a treat to get another move. It's not like Pac-Man, you get an extra life. It's a bad thing. But if you have to complete a box and then move again, there's a total number of m by n boxes that you can create. And if you can't make 2 boxes in one move and you subtract out, and you're kind of resetting. Every time you make as many boxes as you can, you're the first player again. You start all over and you start with your first move again. So every time that you do this, you want to subtract off or reset every time a box is made. But the last box itself is not a reset, right? That's your last box and you're done. So what you really want is this whole sum to end up being odd. So if you didn't understand a word I said, think of it this way. Once you complete your box, let's say you got a box up in the corner like this. It's you, right? You got the box. No matter what's on the scale again, whatever you do on whatever's left, it's a new fresh board for you. You're first player again, and you've made a new, this is done, this is nothing you can touch anymore. So you're now on the whole palette making another first move. So you're resetting. So this last piece over here in red is the reset button. That's resetting the count. So you want that to be odd. And I did a little bit more high school commutative algebra, pulled everything together and factored. And I did this little trick you do in real analysis. Why? Because I was trained as an analyst, so I think like this. So I add 1 and subtract 1. I've really added a 0. So I can factor these 2 pieces over here. So I want this quantity to be odd. But that's the same thing as that 2 not being there at all, right? If you take 2 steps back, 5, take 2 steps back, 3 is odd. So it's the same thing as m minus 1 times n minus 1 being odd. So I really want that product to be odd. But that only happens if m and n are even. And all of this argument works okay as long as I have an even number of double box moves. Double box moves are, you can see, the computer's done it to you because they've done it to me. You have something like this, and they just go like this, and they get 2. Sometimes they get 7 all in a row, right? So you've seen the double box moves. As long as you have an even number of double box moves, this argument works. Well, the number of double box moves that you have is going to be the number of long chains that you have. In fact, that's the whole concept of the long chain, right? They just start putting up the double boxes and getting all of them back to back. So it's going to be the number of long chains that you have and any singleton double box that you have that's of this type. So that means in order to have the first player win, you want to first, in the case m and n are even, you want to force m minus 1 times n minus 1 to be odd. And you want to also have an odd number of long chains to make that whole sum turn out to be odd. And this makes more sense, of course, when you're playing the game. You start seeing these little patterns as you play and get the intuition. So that is a totally red-marked Paryzinski proof. If you haven't had Dr. Paryzinski yet, he's a very careful. He wants to see everything well-defined and everything in order. That was not an example of something that would fly in his class. Okay, so I will come back to dots and boxes to give you more open problems, but I can tell you I'm going to confirm with the game theorist I work with and ask him for certain, but I believe that everything about dots and boxes is pretty much open. What's the optimal strategy for the 4x4 box? I think that's not known. So you could literally just start on dots and boxes and start playing. I don't know what would happen with a 3x3. I don't know if that would make anything interesting. But you could start with small and then build big, or then, as some of you noticed, if the boxes are really big, you find some patterns easily and you're able to win much more easily. Why is that? that's kind of, I don't think anybody's really explored that. You could explore these things. You're gonna have to do a literature search and see what's out there, but I do know a couple game theorists that would be able to tell me what's really known in this area or not. So optimal strategies, as far as I know, are not known. So we'll keep drawing on these games as we go forward. So now we're going to go to one of my favorite games, and that's single pile NIM. So I'm going to break off this video.